Hey everyone, and welcome back to Space Repo, your portal to the cosmos. Today, we're diving into one of the most profound and baffling mysteries in all of science. Imagine everything you see around you, the device you're watching this on, the room you're in, our planet, the sun, and every star you can see in the night sky. All of it, everything we've ever observed directly, makes up less than 5% of the entire universe. The rest? Well, a huge chunk of it is something scientists call dark matter. It's a substance that doesn't emit, absorb, or reflect any light, making it completely invisible to our telescopes and instruments. Yet, we know it's there. So, how can we be so sure about something we can't see? The story begins not with looking into the darkness, but by observing the brilliant light of distant galaxies. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies. He was trying to measure its total mass. He did this in two ways. First, he measured the total light coming from the galaxies, which gave him an estimate of how many stars were there and thus, the cluster's mass. Then, he used a different method. He observed how fast the galaxies on the outskirts of the cluster were moving. The faster they moved, the more gravitational pull was needed to keep them from flying off into space. What he found was shocking. The galaxies were moving far too quickly for the amount of visible matter he could see. Based on their speed, there had to be hundreds of times more mass in the cluster than what the stars accounted for. Zwicky called this missing mass Dunkel Materie, or dark matter. At the time, his idea was largely dismissed, a strange anomaly that many thought would be explained away with better observations. Decades later, in the 1970s, another astronomer named Vera Rubin provided the nail in the coffin for a universe made only of what we can see. She was studying the rotation of individual spiral galaxies, like our own Milky Way. Think about our solar system. The inner planets, like Mercury and Venus, orbit the Sun much faster than the outer planets like Neptune. This is because the Sun contains almost all the mass, and its gravitational pull gets weaker the farther you go. Rubin expected to see the same thing in galaxies. Stars near the bright, dense center should be moving quickly, while stars on the outer edges should be moving much more slowly. But that's not what her data showed. Instead of slowing down, the stars on the outer fringes of the galaxies were moving just as fast as the stars closer to the center. This flat rotation curve made no sense. The only way to explain it was if there was a massive, invisible halo of matter surrounding the entire galaxy, extending far beyond the visible stars. This halo would provide the extra gravity needed to keep those fast-moving outer stars in their orbits. This observation has been repeated for countless galaxies, and the result is always the same. The universe is not what it seems. There is a vast, invisible scaffolding holding galaxies together, and we call it dark matter. The evidence doesn't stop with rotating galaxies. One of the most powerful tools for seeing the invisible is a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. Einstein showed that massive objects can warp the fabric of space-time itself. This means that light doesn't always travel in a straight line. As light from a distant object passes by a massive object, like a galaxy cluster, its path is bent. This acts like a cosmic magnifying glass. The gravity of the massive cluster can distort, magnify, and even create multiple images of the background object. By studying how much the light is bent, astronomers can precisely calculate the mass of the object doing the lensing. And time again, the mass required to create the observed lensing effects is far greater than the mass of all the visible matter. Sometimes, this effect is dramatic. We see giant, stretched-out arcs and ghostly rings of light from distant galaxies, their images warped by the immense gravity of an invisible dark matter halo. One of the most compelling examples comes from a celestial object known as the Bullet Cluster. This is actually two galaxy clusters that have passed through each other in a colossal cosmic collision. When the clusters collided, the hot gas from each cluster, which makes up most of their normal matter, smashed into itself and slowed down, creating a shockwave that we can detect with X-ray telescopes. However, when astronomers mapped the gravitational lensing effect around the colliding clusters, they found that most of the mass didn't slow down at all. It passed right through the collision without interacting. This is exactly what you would expect if the clusters were mostly made of dark matter. The normal matter crashed and burned, but the dark matter, which barely interacts with anything, just kept on going. The bullet cluster shows us a clear separation between where the normal matter is and where the real mass, the dark matter, is located. So, the evidence is overwhelming. From galaxy rotation curves to gravitational lensing and the cosmic microwave background, the universe's oldest light, everything points to the existence of this mysterious substance. It makes up about 27% of the universe's total mass energy content. But that just deepens the mystery. If dark matter is everywhere, holding our galaxy together, what is it actually made of? This is one of the biggest unsolved questions in physics today. The leading theory is that dark matter is composed of a new type of fundamental particle that we haven't discovered yet. These particles would be very different from the protons, neutrons, and electrons that make up you, me, and everything we know. Scientists have given these hypothetical particles a few names, but the most popular candidate is called a WIMP, which stands for Weakly Interacting Massive Particle. Massive means these particles have mass, which is why they exert gravity. Weakly interacting means they barely ever interact with normal matter or with each other, except through gravity. This is why they are so hard to detect. Billions of these WIMPs could be passing through your body every single second, and you would never feel a thing. They are the ultimate ghosts of the cosmos. To hunt for these elusive particles, scientists have built some of the most sensitive experiments ever conceived. They are often located deep underground, in old mines or tunnels, to shield them from cosmic rays and other radiation that could mimic a dark matter signal. These experiments are essentially large, pristine tanks filled with a special substance, like liquid xenon or supercooled crystals. The hope is that, just once in a very rare while, a WIMP will bump into the nucleus of an atom in the detector, creating a tiny flash of light or a faint vibration that can be measured. Despite decades of searching, these direct detection experiments have not yet found a definitive signal of a WIMP. The hunt is still on, with each new experiment becoming more and more sensitive, pushing the boundaries of what we can measure. Another way to find dark matter is to try and create it ourselves. At the Large Hadron Collider at CERN, physicists smash protons together at nearly the speed of light. The idea is that these high-energy collisions could produce new, undiscovered particles, including dark matter particles. Since these particles would be invisible to the detectors, scientists look for missing energy. If the energy after a collision is less than the energy before, it might mean that some of the energy was carried away by invisible dark matter particles that flew out of the detector unseen. So far, like the direct detection experiments, these searches have come up empty, but they have helped us rule out many possibilities. Given the lack of direct evidence for WIMPs, some scientists are exploring other, more exotic possibilities. One idea is a particle called the axion. Axions are predicted to be incredibly light and would have been produced in enormous quantities in the early universe. Another theory suggests that dark matter might not be a new particle at all. Perhaps our understanding of gravity is incomplete. These modified gravity theories propose that on very large, galactic scales, gravity behaves differently than Einstein's theory predicts. In this view, there is no missing mass. The strange rotation of galaxies is simply a sign that we need a new theory of gravity. However, these theories have had a hard time explaining all the evidence, especially the clear separation of mass seen in the bullet cluster. For now, the mystery endures. Dark matter remains a shadow cast across the cosmos, a constant reminder of how much we still have to learn. It is the invisible force that sculpted the universe, allowing galaxies to form and providing the cosmic web upon which the grand structure of the universe is built. Without dark matter, the stars, the planets, and we ourselves would likely not exist. Uncovering its true nature will not only solve a cosmic puzzle but could also usher in a revolution in our understanding of fundamental physics. What do you think dark matter could be? A new particle, a flaw in our theory of gravity, or something even stranger? Let me know your thoughts in the comments below. Thanks for joining us on this journey into the dark. If you enjoyed this exploration and want to learn more about the universe's greatest mysteries, make sure to subscribe to Space Repo and hit that notification bell. We'll see you in the next one.